Now let's talk about change of basis. So far, we have learned that a matrix represents a linear transformation. But here's something surprising. The same transformation can have different matrices. How? Because matrix depends on the basis we choose. Let's see and go through some code that you will understand it more better. Instead of describing vectors using the standard basis, let's choose a different basis. And these basis vectors become the columns of the change of basis matrix. Here we transform the basis vector. We also need the inverse of the change of basis matrix. Here we have performed the change of basis matrix. Now compute the inverse. Now here comes the most important question in this section, and this gives us the matrix of the same transformation in the new basis. Amazing, right? Look at the original matrix and it becomes new matrix like this one. And we didn't change the transformation. We only changed the basis. So let's verify that both matrices perform exactly the same transformation. Here, we'll get original transformation. And now we'll do the same transformation using the new basis. And after running this code, we'll get this converted matrix. Notice that the final answer is exactly same whether we use the original matrix or the transformed matrix. The result doesn't change. The only thing that changed is coordinates of system. The new matrix is a diagonal, look at here. And diagonal matrix is much easier to work with. Instead of mixing coordinates, it simply scales each coordinate independently. This is why we often look for a basis that diagonalize a matrix. Later, when we study eigenvalues and eigenvectors, we'll learn exactly how to find such a basis. Now, after running this code, we'll get some visualized graph of basis. Look at here, standard basis, new basis and transformation of basis. Finding the right basis is the one of the most powerful ideas in linear algebra. Many machine learning techniques like PCA, eigenvectors, decomposition are based on choosing a basis that makes the transformation as simple as possible. Changing the basis doesn't change the transformation, it only changes how we describe it. Sometimes the right basis can turn a complicated matrix into a simpler one, making computations easier and revealing the hidden structure of the transformation. Now here comes geometric linear transformations. A matrix represents a linear transformation. But what does the transformation actually looks like? Instead of thinking about numbers, let's think about geometry. A linear transformation doesn't just move a single vector, it transforms the entire space. That's the geometric nature of linear transformation. In two dimensions, there are five fundamental linear transformations that we'll study, which is stretching, rotation, shearing, reflection, projection. Let's go through code step by step. Linear transformation is stretching. Instead of scaling every direction equally, stretching allows us to scale the x-axis and y-axis independently. If one value is larger than 1, then vectors stretch, and if it's between 0 and 1, vectors shrink. Notice that the unit square becomes a rectangle but straight line remains straight in this code. Now second comes here, which is rotation script. Rotation changes only the direction of vectors. Their lengths stay exactly the same. Every point rotates around the origin by the same angle. That's why rotation preserves the distances and angles. Here's the shearing point. Shearing is different. It doesn't simply rotate or stretch the vector. Instead, it slides one side of the shape while keeping the opposite side fixed. So the square becomes parallelogram. And this type of transformation appears frequently in computer graphics and physics. Now let's see the reflection. Reflection flips the entire space across an axis, just like looking into a mirror. Left becomes right and up becomes down. Depending on the reflection matrix, reflection changes the orientation of space. And the linear transformations can also be combined here. We first reflect the space and then rotate it. And the result is a completely different transformation. But it's still represented by a single matrix. These transformations are not only important for building intuition, they are also widely used in computer vision and machine learning. For example, when training an image classification model, we often rotate, flip, or stretch images to create new training examples. So, this process is called image augmentation. and it helps models generalize better. The final geometric transformation we'll study is called orthogonal projection. Imagine shining a flashlight straight down onto a line. Every vector creates a shadow on that line. That shadow is called a projection. Projection keeps only the part of the vector that points in the chosen direction. Everything perpendicular to that direction is discarded. This idea is extremely important in machine learning. Algorithms like principal component analysis project high dimensional data into lower dimensional spaces while preserving as much useful information as possible. Instead of keeping the whole vector, we keep only part that lies in a particular direction. Everything perpendicular to that direction is removed. Now let's ask one question. How much does a transformation change the size of shape? Imagine drawing a unit square on the coordinate plane. Now apply linear transformation. The square may become larger, smaller, or even collapse into a line. The amount by which its area changes is measured by a single number called determinant. If the area doubles, the determinant is 2. If the area is cut in half, the determinant is 0.5. If the square collapses into a line, then determinant will be 0. In one line, a determinant is the scaling factor of area in 2D or volume in 3D produced by linear transformation. Now we'll see how linear transformation scale the area. A determinant tells us how much a linear transformation changes the area or volume. Imagine drawing a unit square and its area is exactly 1. Now apply a linear transformation. The square changes into parallelogram. The area of this new shape tells us how much the transformation scaled the space. That scaling factor is called the determinant. Example 1. Suppose we stretch the square twice along the x-axis. Before, the area was 1 and after stretching, area would become 2. The determinant is 2 because the area is doubled. So let's talk about next example, which is shrink. Now shrink the square before area is equal to 1 and after area becomes 0.5. So the determinant will be 0.5, and in collapse the square has no area anymore. Area becomes 0, so determinant becomes 0. Whenever the determinant is 0, the transformation loses the information and cannot be inverted. What does a negative determinant mean? Sometimes the area stays the same, but the transformation flips the space like looking in the mirror. The area is unchanged, but orientation flips. The determinant becomes negative. Now, how would I calculate it through a formula? The determinant formula isn't something mathematicians invented randomly. They first asked, how can we calculate the area of parallelogram formed by two columns vectors? After working, after working through geometry, the answer turns out to be remarkably simple. So, don't think of AD minus BC as just a formula to memorize. Think of it as a shortcut for computing how much a linear transformation scales area. There are many ways to calculate the area of parallelogram. In school, we learn base into height, and in trigonometry, we learn the length into length and the sine theta. So in linear algebra, we use the determinant. All three methods gives exactly the same area. The determinant isn't a new concept. It is simply a clever shortcut that computes the same area directly from matrix entries. So in most ML algorithms, we do not calculate the area directly. Instead, we calculate the determinant of the transformation matrix because the determinant already tells us how the transformation changes area or volume. Why do we care about area? Imagine you have a data set which is you can see in the screen. So before transformation, the data would look like this, and after applying a linear transformation, we'll see the data like this. And the point have moved. Now ask, did the data spread out? Did it shrink? Did it flip? Or did it collapse into a line? So the determinant answers all of these questions. In principal component analysis, suppose your data is this and PCF projects into one direction. Area becomes almost zero. This means redundant information removed from lower dimensional representation. So in machine learning, we rarely compute the area of transformed data directly. Instead, we compute the determinant of transformation matrix. The determinant tells us how much the transformation stretches, shrinks, or collapses the data space. This becomes essential in PCA, Gaussian distribution, covariance matrices, normalizing flows, and invertible neural networks. Now let's look at the sum of its most important properties. First, product rule. Suppose we apply two transformations one after another. First transformation B, then transformation A. The combined transformation is simply A into B. Now think about what happens to the area. If B doubles the area and then A triples it, the final area becomes 6 times larger. So this gives us one of the most important properties of determinants. In simple words, the total scaling factor is the product of individual scaling factors. Number 2, inverse matrix. What happens if we apply transformation and then immediately undo it using its inverse? Nothing changes. The overall scaling factor must be 1. So if a transformation doubles the area, its inverse reduces the area by half. Third one is similar matrices. Earlier, we learned that same linear transformation can have different matrix representation. When we change the basis, these matrices are called similar matrices. Although the matrices look different, they represent the same transformation. So their determinants are also the same. Changing the basis does not change the determinant. Number 4, swapping rows or columns. If we swap any two rows or any two columns of matrix, the orientation of the space flips. The area stays the same, but the determinant changes its sign. Positive becomes negative and negative becomes positive. Number 5, determinant equals 0. One of the most important properties is this. If the determinant is 0, the transformation collapses the space and a square becomes a line or a cube becomes a plane. Information is lost, so the transformation cannot be reversed. 6.1, linear dependence. If the two columns of a matrix point in the same direction or one is just a multiply of other, they are called linearly dependent. In that case, they cannot span the full space. The transformed area becomes 0 and therefore the determinant is also 0. Number 7, determinant and invertibility. Finally, here's the most important takeaway. If determinant of A is equal to 0, the transformation is invertible. So no information is lost and we can recover the original data. But if determinant is equal to 0, the transformation is not invertible because different vectors collapse onto the same output. So remember these key properties. The determinants tells us how much a transformation scales area or volume. The determinant of a product is the product of the determinants, and the determinant of an inverse is the reciprocal of the original determinant. Swapping two rows or columns changes the sign of determinant. A zero determinant means information is lost. Now, please go through recap points and I'll see you in the next video.